Hello everybody, and welcome to this series that I'm about to make about how computers work. This series is heavily inspired by a creator named Sebastian, and he made this digital logic simulation in order for him to explore how computers work. But his series is a little flawed because he doesn't go over everything about how computers work, nor does he optimize transistor count and logic count on how computers work. Nevertheless, he does show a very detailed explanation about how all of these logic gates come together to form complex math and to hold values in memory. But I think we can go a little deeper than this and what he did on his. So we're going to make our own 4-bit digital CPU in the same simulation that he made and explore how we can optimize for transistor count. So if we want to build this in real life, we're using the fewest amount of transistors, which would save us money, and we're also going to explore other components of the CPU like a JK flip-flop and a program counter and other ways we could do math on binary values. So let's get started. So this is a simulation right here. We're going to press new project. I'm going to call it 4-bit CPU. So the way it starts off is we have this one gate called an AND gate. And let's see what it looks like. So when both of the inputs are off, the output is on. And when one of them is on, the output is still on. But when both are on, the output turns off. And it turns out that this one single gate is all you need to make a computer. This one gate right here can make any other gate possible known to man. So that's why the simulation, when you start off, it only gives you this one gate, because this is all you need. So let's make this gate into a NOT gate real quick. And what is a NOT gate? So it pretty much just inverts the input. So the input is off, the output is on, the input is on, the output is off. So this is an AND gate. So as you can see, the output is off. If one of them are on, the output is still off. But if both of the inputs are on, the output turns on. So if A and B are on, then C turns on. And this is very useful too. So we're going to say this as an AND gate. So this right here is an OR gate. So as you can see, if both the inputs are off, the output is off. But if one of them are on, the output turns on. And if both are on, the output still is on. So this is an OR gate. Because either OR can be on for the output to be on. And then this is a NOR gate. So the output is on if both the inputs are off. But as soon as one of them turns on, the output turns off. Now this gate is where it starts to get a little interesting. So both inputs are off, so the output is off. But as soon as we turn one or the either one on, the output turns on. But if both of them are on, the output turns off. So this gate is called an XOR gate. and it's very useful. So we hook up an XOR gate to a NOT gate, we get the inverse of a regular XOR gate, which will turn on when either one is on, but not when both is. So this is an XNOR gate. So the output is only high if both the inputs are the same. But as soon as the inputs become different from each other, the output turns off. And this will also come in handy quite later. So there we go. These are all the basic gates that we have. So the NAND, NOT, the AND, the OR, the NOR, the XOR, and the XNOR. So let's go over transistor count for each of these and how they work. So I have a past video where I made a small basic computer system with discrete transistors. So unlike a normal CPU in your laptop, it uses a special transistor called a MOSFET. And a MOSFET uses voltage to control whether the gate is on or off. But the computer system I made is made with TTL transistor logic, which stands for transistor logic. And that uses current to turn the transistors on and off. And the main reason I did that is because it's cheaper. It's cheaper and a lot easier to use. So we're going to base this computer system off of transistor logic, or TTL logic systems, because I'm not too familiar with how a MOSFET CPU would work. So with that in the back of our minds, let's go over how many transistors it takes to make each of these core gates. So the NAND gate and the NOR gate are going to get their own little category, and they take 2 transistors to make. The NOT gate takes 1. The AND gate and the OR gate take 3 transistors to make. And the XOR gate takes 7. And the XNOR gate will take 6. So, in order to optimize everything that we've made, we want to try to use these gates as much as possible and try to exclude the XOR and XNOR gates. But sometimes it is inevitable that we'll have to use it. And I don't know if you remember, but let's see what the XOR gate looks like. It uses 8 NAND gates. So if we made this with transistors, this would take, it uses 4 NAND gates. It would take 8 transistors to make using NAND gates, but we can make a slightly more efficient design of an XOR gate that uses 7 transistors, but it's not made up of 4 NAND gates. It uses a different logic system that works with transistors. So this is a little demonstration I made of an AND gate. As you can see, both the inputs are off, the output is off. I can press either one on, and when I press them both, the output becomes on. And it works using these little transistors right here. So we have the inputs are connected to these 2 resistors to limit the amount of electricity going into these little low power transistors. And then this transistor is hooked up to the power supply. And once we press the buttons, we allow them to open up their gates, and it allows current to flow from the power supply into the LED. And then we can hook this up to different outputs in order to process the signal. But it works just like how it does in our simulation. Now, using a very similar setup with only 2 transistors, we can make the NAND gate. And remember, this gate
can be used to make any other gate we can think of. So, right? So when I press either on, the output is still on, but as soon as I press both, the output becomes off. And then we can use these transistors to make all the other gates.
So let's get started with the most basic circuit that all computers use, the adder. The half adder, to be more specific. So a normal half adder uses an AND gate and an XOR gate. I forgot one output. Give me a second. So if one of them are on, it goes to the sum, and if both are on, it goes to the carry. So we can carry the number over. And it's made with an AND gate and an XOR gate. So total, this would be 10 transistors just to make a half adder. We can simplify it down just a little bit, and here's how we're going to do it. And this is going to give us our sum. So, see? But this also has this NAND gate in the middle right here. And this is just a reverse AND gate. So if we put a NOT gate right here, just to invert the signal to make it into a normal AND gate, we get an adder right here. See? And it gives us the exact same logic as the other gate, except now we're saving a transistor pretty much, so it's a little more optimized. So this uses 8 transistors right here, this XOR gate, and then this uses 1 transistor to make the NOT gate. So in total this is 9 instead of 10. So you might be thinking, this really doesn't save us that many transistors in the long run, and you're right, it's only 1 transistor. But if you want to make a big adder to add multiple bits, this could save you a good bit in the long run. So we're going to save this chip as our half adder. So if we go look at the half adder again real quick, you can see that we only have these 2 numbers, and it makes a sum output and then a carry output. But this system is a little flawed. So let's take a second to look at how to add binary numbers versus how we add digital numbers. And then we'll get back to the logic system in a second.
Okay, so let's look at how addition works with binary numbers. Right? So let's say we're adding number 9 plus the number 5. So we do this in decimal system. We get 9 plus 5 is 4. And then we don't have a number that represents 14, so we have to carry the 1. And of course there's 2 zeros here understood. So we have 1 plus 0 is 1. So we get 14. So once we go over the 10 threshold, we have to carry the 1. The same thing is true with binary, but instead of the 10 being the threshold, 2 is now the threshold. So 1 plus 1, we're over the threshold now because it's 2. So we could put 0 and then 1. So then 1 plus 0 plus 0 is 1. 0 plus 1 is 1. And then 1 plus 0 is 1. So we get 14.
So we add binary numbers. We're going to need a carry input for the carry, and then the two numbers that we're adding, just like a base 10 system. So we're going to need two half adders, hence why they're called half adders, and then an OR gate to combine. So okay, so it looks like it works. So let's go over it again real quick. So A, or B, plus A will give us this little carry. And then if the carry in is also on, the sum comes on. So it looks like it's working. So we're going to save this as a full adder. Okay, so this is our full 4-bit adder. And it might look a little strange if you look at other adders, because we only have two actual full adders, or fuller adder, I guess, as I put it. And then we have a half adder, and then these two XOR gates. And you might be thinking, well, these XOR gates, aren't they using a lot of transistors? Shouldn't we switch them out? And yes, they are, but this is the most simplified that I can think of as of right now. So let's look into it. So 1 plus 1 would give us 2, right? 2 plus 1 gives us 3. 4 plus 1, 4 plus 2 will give us 6. 4 plus 1 will give us 5, and so on. So it looks like the systems work. But let's say we get an overflow error, right? 8 plus 8, it turns off. So since there's an only 4-bit output, we don't really need a carry out from our full adder, because there's nowhere for us to display this data. So all we need is these two XOR gates to determine whether the 8's on or off, which saves us a little bit of logic, because we look at this, we save an OR gate, and we save on our little AND gate system right here. So all we need are these two XOR gates. But if we want to be able to expand more in the future, we could add a full adder right here, because then we'll have that carry out pin for access for whenever we need it. And the same thing can be said for this little half adder, except there really is no reason for us to have a full adder right here, because the half adder doesn't have to carry in, and what is there to carry? So we only have this 1 on both sides, and there's no number before 1, so we don't need to carry in any input before the first input. So all we need is a half adder for the system. And let's do a little quick math to see how many transistors this will take. So just this system right here will take 65 transistors in order to make it. To make a basic 4-bit adder takes 65 transistors, which is kind of crazy. But Since transistors are the size of nanometers, we can add billions of them into a CPU die that is used to process the simulation right here. But we're going to save this chip and call it our 4-bit adder. And this video is getting kind of long, so next video we're going to talk about how we can compare two numbers to make a comparator, subtract two numbers to make a subtractor, and we might get a little bit into the GPU, or we might get into how we can store data. But that's it for this. See you in the next one.